Now in this lecture I answer two questions. In the first question we find out the area of this pentagon ABCDE, and in the second question we find out the area of this grand shape. So we start with the first question. What is a pentagon? Pentagon is a flat closed shape with 5 straight sides and 5 interangles. This is pentagon ABCDE. It has 5 sides, 1, 2, 3, 4, 5, and 5 interangles. 1, 2, 3, 4, 5. So, in the drawing we have pentagon ABCDE. We know that side ED equals to 1 unit in its length, side EA equals to 1 unit in its length, side BC also equals to 1 unit in its length, side DC equals to x units in its length, side AB equals to 1 minus x units in its length. This is the angle EAB, this is a right angle, and this is angle EDC, this is also a right angle. Again, our task is to find out the area of this pentagon ABCDE. So first of all, we'll join points E and B together by a straight line. And we join also points E and C together by a straight line. In the next step, we'll extend side BA. We'll extend side BA of pentagon ABCDE by a straight line in such a way that the extended part will be equal to x units in its length. We define this point as point M. In the end at AM, the extended part AM is equal to x units in its length according to our construction. When you extend a straight line by a straight line, the result is a straight line. You extended a straight line BA by a straight line, and therefore the result BM is a straight line. So if you focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? We have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we join points E and M together by a straight line. And we will prove that those two right angles are similar to each other according to side angle side rule. So we also prove that the right line EAM can weld to this right line EDC. So why those two right angles can go into each other? First of all, side AM on the right angle EAM is equal to side DC on the right angle EDC. They are both equal to X and therefore they are equal to each other. So maintenant, AM equals to DC and again side AM on the right angle EAM equals to side DC on the right angle EDC. They are both equal to X and therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees and therefore they are equal to each other. So this is angle EAM in the right angle EAM. It is equal to this angle, is actually angle EDC in the right angle EDC. And again, angle EAM in the right angle EAM equals to angle EDC in the right angle EDC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, side EA of the right angle EAM equals to side DE in the right angle EDC. They are both equal to 1 and therefore they are equal to each other. So right now, side EA of the right angle EAM is equal to side ED of this right angle EDC. And again, side EA of the right angle EAM is equal to side ED of the right angle EDC. They are both equal to 1 and therefore they are equal to each other. So we actually prove that those two right angles can go into each other according to side angle side rule. So we can prove that the right angle EAM congruent, this is the sign of congruent, to the right angle EDC according to side angle side rule. That is to say, I shall prove that those two sides and the angle that is included between those two sides, right angle, in the right angle EAM are corresponding equal to those two sides, and the angle that is included between those two sides, that is a right angle, in the right angle EDC. And therefore those two right angles can go into each other according to side angle side rule. And from the fact that they can go into each other, we will derive that they have also the same areas. That is to say, the area of triangle EAM is equal to the area of triangle EDC. Write it down. The area of triangle EAM is equal to the area of triangle EDC. Any two triangles that can go into each other, they must have also the same areas. So if we define the size of angle of triangle EDC as S, that is to say it is equal to S corresponding inside, then the size of triangle EAM must be also equal to Z corresponding inside, because they are equal to each other and they have the same areas. So the area of this right green triangle EAM is equal to this right triangle EDC. So if you define this triangle EDC as Z, then the outside EM must be also equal to Z, so this is inside because they have the same areas. What is the length of side line segment MB or side A MB? MB in total equals to MA plus AB. So write it down. MB equals to MA plus AB. So MB in total equals to AM, that is X, plus AB, that is 1 minus X. So in total MB equals to X minus X is 0, so we're left only with 1. So MB equals to 1 unit in its length. MB equals to 1 unit in its length. In the next step, we'll prove that triangle AMB can go into this triangle EBC according to side wall. So we have to prove that this is triangle MEB. We have to prove that triangle MEB can go into this triangle EBC according to side wall. So why those two triangles can go into each other? First of all, side MB of the triangle EMB is equal to side BC of the triangle EBC. They are both equal to 1 and therefore they are equal to each other. So write it down. Side MB of triangle MEB is equal to side BC of triangle EBC. Again, side MB of triangle EAM. It's actually triangle MEB or EBM. It's triangle EBM. So side MB of triangle EBM is equal to side BC of triangle EBC. So triangle EBC. And again, side MB of triangle EBM is equal to side BC of triangle EBC. They are both equal to 1 and therefore they are equal to each other. In addition, before I continue, because of the fact that those two right triangles can go into each other, we will derive that EM is equal to EC. EM equals to EC according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides, that is to say EM and EC, must be also equal to each other in the reverse. So EM equals to EC. We continue to prove that that the right triangle EBM can run to the right triangle EBC according to side rule. So those two sides, they are equal to each other. So side EEM of triangle MEB is equal to side EC of triangle EBC. Side EM of triangle EBM is equal to side EC of triangle EBC. So again, we just find the formula that side EM of triangle EBM is equal to side EC of triangle EBC. And finally, EB is a common side that belongs to both triangles. You can see that EB belongs to triangle EBM and EB also belongs to triangle EBC. So you can write down that EB equals to itself is a common side that belongs to both triangles. And again, EB equals to itself as a common side that belongs to both triangles. So let's prove that all the three sides of this triangle MEB are correspondingly equal to all the three sides of this triangle EBC, and therefore those two triangles can go into each other according to side rule. So if you don't know that triangle MEB convert, this is the sign convert to triangle EBC according to side rule. And from the fact that those two triangles can go into each other, we will derive that they have also the same areas. That is to say, they have this side EBM equal to they have this side EBC. And the two triangles that can go into each other, they must have also the same areas. Again, the outside EBM is equal to the area of triangle EBC because they can go into each other. So in the next step, we calculate the area of this triangle MEB. You know that the area of any triangle equals to the base of the triangles times the height over 2. Therefore, the area of this triangle MEB will be equal to the base MB times the height AE over 2. See again, the area of triangle EBM equals to the base MB times the height AE over 2. MB equals to 1. The height AE also equals to 1, and we have to divide it by 2. So in total, I should have found out that the area of triangle EBM equals to 1 times 1 over 2. 1 times 1 is 1, so in total the area of triangle EBM equals to 1 half. The area of triangle EBM equals to 1 half. So we know that the area of triangle EBM is equal to the area of triangle EBC, and therefore the area of triangle EBC must be also equal to 1 half. It's constant in its size, so they have the same areas. So the area of this triangle EBC must be also equal to 1 half, because they have the same areas. So therefore the area of triangle EBM plus the area of triangle EBC will be equal to 1 half plus 1 half, that is 1. So as you know, the area of triangle EBM plus the area of triangle EBC equals to the area of triangle EBM is 1 half, plus the area of triangle EBC is also 1 half. So 1 half plus 1 half is 1. What is the area of the big quadrilateral EMBC? Quadrilateral EMBC consists of two shapes. It consists triangle EMB and it consists also triangle EBC. And therefore, the area of the big quadrilateral EMBC will be equal to the sum of the areas that it consists of, to the sum of the areas of the shapes that it consists of. That is to say, it will be equal to the area of triangle EMB, that is 1 half, plus the area of triangle EBC, that is also 1 half. Therefore, in total, it is equal to 1. In the end, the area of triangle EMB, the area of quadrilateral EMBC equals to the sum of the areas of the two shapes that it consists of. That is to say, it is equal to the area of triangle EBM plus the area of triangle EBC. So we found out that the area of triangle EBM equals to 1 half, plus the area of triangle EBC that is also equals to 1 half. 1 half plus 1 half is 1. So we found out that the area of the big quadrilateral EMBC is equal to 1 half squared in size. And again, the area of the big quadrilateral EMBC equals to 1 half squared in size. But the big quadrilateral EMBC consists of two other shapes. It consists of this green triangle EMA plus this quadrilateral EABC. And the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of this green triangle EMA plus the area of this quadrilateral ABCE. And from this equation, we will derive that the area of the ring right triangle EMA plus the area of quadrilateral ABCE equals to 1. Okay? So in the norm, we found out that the area of the green right triangle EMA plus the area of quadrilateral ABCE is equal to 1. But according to our definition, the area of triangle EMA equals to Z squared inside. So we substitute the area of triangle EMA by Z plus the area of triangle quadrilateral ABCE is equal to 1. So if we found out that Z plus the area of quadrilateral ABCE equals to 1 squared in size. Our task is to find out the area of this pentagon ABCDE. The area of pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. Pentagon ABCD consists of this great right triangle EDC, and it also consists of this quadrilateral ABC, and therefore the area of pentagon ABCD will be equal to the area of this right triangle EDC plus the area of this quadrilateral ABCE. So later on, the area of pentagon ABCE is equal to the area of this great right triangle EDC plus the area of this quadrilateral ABCE. Consists of those two shapes only, and therefore the area of pentagon ABCD must be equal to the sum of the areas of the two shapes that it consists of. So if you found out that the area of pentagon ABCD equals to the area of the right triangle EDC plus the area of quadrilateral ABC. But according to our definition, the area of triangle EDC equals to Z squared inside. So I can substitute the area of triangle EDC by Z plus the area of quadrilateral ABCE. But we already found out that, so the area of pentagon ABCD equals to Z plus the area of quadrilateral ABC. But we already found out that Z plus the area of quadrilateral ABCE equals to 1. So we can write here that Z plus the area of quadrilateral ABCE equals to 1. And from this long equation, we derive that the area of pentagon ABCE equals to 1. This is the answer to the first question. One square is in size. So if you want to know that There are this big pentagon ABCDE, that is the area that we are looking for in this question. It is equal to 1 square inch in its size. So we finish with the first question. The next step, I'll present you the second question. And so the second question of this lecture. In the second question, our task is to find out the area of this green shape. The green shape is actually triangle A and B, so we have to find out the area of this triangle A and B. So in the drawing we have a circle. Inside this circle we have triangle A and B. This is the green shape actually. The green triangle A and B is the green shape. In addition, we know that AB is the diameter of this circle. So later on, AB is the diameter of the circle according to what is given in the question. In addition, we know that line segment AP equals to 9 units in its length, line segment DQ equals to 4 units in its length, and PQ, line segment PQ is tangent to the circle at point M. Again, our task is to find out the area of the green shape, that is actually the green triangle A and B. So first of all, we can implement here rule 7. So repeat quickly on rule 7. According to rule 7, if a peripheral angle is subtend on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. Chord AB is the diameter of this circle. This is peripheral angle ACB that subtend on chord AB. This is the diameter of this circle. And according to this rule 7, any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle ACB must be equal to 90 degrees in its size. So we can implement rule 7 in our drawing. Now we put in our drawing, we have peripheral angle A and B that subtend on the diameter of the circle, and therefore is equal to 90 degrees in its size. AB is the diameter of the circle. In the next step, we define angle PAM. This angle is alpha. So in the right triangle APM, this angle equals to alpha. This angle equals to 90 degrees according to what is given in the question. This angle also equals to 90 degrees according to what is given us in the question. So this angle equals to alpha, this angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. It is given as a question that PQ is a straight line. PQ is definitely a straight line because PQ is a tangent to the circle at point M, and we know that any tangent is absolutely a straight line. So PQ is a straight line. If we focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? We have this angle that is 90 degrees minus alpha plus this angle that is 90 degrees plus this missing angle BMQ. Total must be equal to 180 degrees according to rule 3. So right now if you found out that according to rule 3, the sum of the angles from the upper side of the straight line PQ point M must be equal to 180 degrees. Like I said, we have in the upper side of PQ at point A, we have 90 degrees minus alpha, plus this angle, that is the right angle, plus this angle, plus this angle BMQ. In total, they must be equal to 180 degrees according to rule 3. Repeat again. The sum of the angles on the upper side of the straight line PQ at point A must be equal to 180 degrees. The angles that we have at the upper side of PQ at point A are as follows. We have 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ. In total must be equal to 180 degrees according to rule 3. 90 degrees plus 90 degrees is 180 degrees plus the missing angle BMQ minus alpha. Total must be equal to 180 degrees according to rule 3. We have 180 degrees on both sides of this equation, so 180 degrees will get cancelled. And we'll have to only if angle BMQ, the missing angle, minus alpha equals to 0. Here we add alpha to this equation. And we get that the missing angle BMQ is equal to alpha degrees in its size. This is the missing angle BMQ, this is equal to alpha degrees in its size. So in the right small triangle BMQ, this is the right small triangle BMQ. This angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the rule that the sum of the angles in the triangle is equal to 180 degrees. It's very easy to see that those two right triangles can point to each other according to angle similarity rule. Anyway, you want those two right triangles are similar to each other. That is to say, the right big triangle APM is similar to the right triangle BMQ. Those two angles are both equal to alpha and therefore they are equal to each other. In addition, both those two angles are equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you find out that all the figures of the big right triangle APM are corresponding equal to all the figures of this small right triangle BQM, and therefore those two right triangles are similar to each other according to angle similarity rule. So, okay, now. I should prove that the right big triangle APM is similar, this is the sign of similar, to the right small triangle BMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AP of the big right triangle APM over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM over side BQ of this small right triangle BMQ. Repeat again. From the fact that those two right triangles are similar to each other, regard that the following relationship exists between their sides. Regard that side AP of the big right triangle APM over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM over side BQ of the small right triangle BMQ. According to what is given as the question, side AP equals to 9 units in its length. So AP is 9 over MQ. MQ is the missing side, so units it is. And it is also equals to PM. PM is the missing side, so units it is. Over BQ. BQ equals to 4 units in its length. So in total, we have found out that 9 over MQ equals to PM over 4. Here we will cross multiply this equation. And we get that 9 times 4 is 36 equals to MQ times PM. So MQ times PM equals to 36. In the next step, we will define the center of this circle. This point is point O. OA is of course the radius of the circle. We define the radius of the circle as R. So OA equals to R. OB is also equals to R. It's in the radius of the circle. In the next step, we will join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself. It's actually the point of tendency of tangent PQ with this circle. Therefore, OM is the radius of the circle. This equals to R. Here we can implement rule 1. Why? Because the radius OM that is equals to R, the radius OM is drawn to point M, that is the point of tendency PQ with this circle. And whenever the radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees in its size according to rule 1, of course. In the next step, we will do a construction. That is to say, from point O, that is the center of the circle, we will do a perpendicular on side AP, or line segment AP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP. This point is point L. By doing this construction, we created the big quadrilateral LOMP. Inside the big quadrilateral LOMP, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, it must be equal to 360 degrees according to the rule. It says that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral LOMP we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must meet its rectangle plus a square. So relate to quadrilateral LOMP is a rectangle because it has 4 right angles. Like you know, quadrilateral LOMPM is a rectangle according to rule 5. In the next step, we will do another construction. That is to say, from point B, we will go perpendicular on the radius OM. Again, from point B, we will go perpendicular on the radius OM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in the radius OM, this point as point S. By doing this construction, we're going to do the small quadrilateral SBQM. Inside the small quadrilateral SBQM, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. And therefore quadrilateral SMQB is a rectangle according to rule 5. So this is the big rectangle LOMP, this is the small rectangle SBQM. We know that the opposite sides of a rectangle are parallel to each other. Okay, again, the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP is parallel to the opposite side OM. Again, in rectangle LOMP, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, then the straight line AP itself must be also parallel to the other straight line OM. Therefore AP is parallel to OM. And again, if a part of the straight line is parallel to another straight line, then the straight line itself must be also parallel to another straight line. That is to say, AP is parallel to OM. AP is parallel to OM. So in the next step, I'll copy the two parallel lines, AP and OM, and then you measure also the diameter A or B, and we implement all 50 in the drawing. Here AP is parallel to OM. AOB is the radius of the circle that cuts the parallel lines at points A and point O. Those two angles are defined as corresponding angles, and they are located between the parallel lines AP and OM, and therefore they are equal to each other in their sizes, according to Rule 50. Rule 50. According to Rule 50, corresponding angles between parallel lines are equal to each other. Here in the drawing we have line A that is parallel to line B. Those two angles, alpha and beta, are defined as corresponding angles, and are located between the parallel lines A and B, and therefore they are equal to each other in their sizes. That is to say, alpha equals to beta. So as I mentioned, you can implement Rule 50 in our drawing. We have here those two corresponding angles are located between the parallel lines AP and OM, must be equal to each other in their sizes, according to Rule 50. So if we define the size of this angle as beta, that the size of this angle must be also equal to beta, because they are equal to each other. So if we found out that angle PAO is equal to beta, angle angle MOB is also equal to beta. So angle PAO equals to beta. This is angle PAO is equals to beta degree in its size. Angle PAO equals to beta degrees in its size. Likewise, angle MOB is also equal to beta degrees in its size. So, in the right triangle ALO, this angle equals to beta. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. Likewise, the green triangle OSB, this angle equals to beta. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta, according to the sum rule that says that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we will prove that this right triangle ALO can go into this right triangle OSB according to angle side angle rule. So why those two right triangles can go into each other. We have to prove that the right triangle ALO can go into this right triangle OSB according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to beta, and therefore they are equal to each other. So this is angle LAO, in the right triangle LAO, and it is equal to this angle, the angle SOB, in the right triangle OSB. Read again. Angle LAO in the right triangle ALO equals to angle OSB in the right triangle SOB. They are both equal to beta and therefore they are equal to each other. AO equals to OB. They are both the area of the circle is equal to R and therefore they are equal to each other. Side AO of the right triangle ALO is equal to side OB of the right triangle OSB. Again, side AO of the right triangle ALO is equal to side OB of the right triangle OSB. They are both the radii of the circle that is equal to R and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta and therefore they are equal to each other. So this is angle AOL in the right triangle ALO, and it is equal to this angle, this is actually angle OBS in the right triangle OSB. Repeat again. Angle AOL in the right triangle ALO is equal to angle OBS in the right triangle OSB. They are both equal to 90 degrees minus beta and therefore they are equal to each other. So we should prove that those two right triangles can go into each other according to angle side angle rule. So as you know, we should prove that the right triangle ALO congruent, this is the sign of congruent, to the right triangle OSB according to angle side angle rule. That is to say, we prove that those two angles and the side that is included between those two angles, that is R, this triangle ALO, are correspondingly equal to those two angles and the side that is included between those two angles that is also R in this right triangle OSB. And therefore those two right triangles can go into each other according to angle side angle rule. We have two sides and the side that is between them, this triangle ALO, that are equal to those two angles and the side that is included between those two angles in the right triangle OSB. And therefore those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that side ALO of the right triangle ALO is equal to side SB of the right triangle OSB. So until now, we derive that LO equals to SB. According to the rule that corresponding sides and congruent triangles are equal to each other, those two right triangles can go into each other, and therefore the two corresponding sides, that is to say LO and SB, must be also equal to each other in their lengths. So if we define the length of this, if we define side LO as X, then side SB must be also equal to X because they are equal to each other. We have the rule that the opposite sides of a rectangle are equal to each other. So the opposite sides of a rectangle are equal to each other. So in the big rectangle LOMP, side LO is equal to the opposite side PM. But LO is X, therefore the opposite side PM must be also equal to X units in its length. Likewise, in the small rectangle SBQM, side SB must be equal to the opposite side QM. but SB is x, therefore the opposite side QM is also equal to x units in its length. We already found out that 36 equals to MQ times PM. So MQ times PM equals to 36. MQ is x times PM is also x. And again, we already found out that MQ times PM equals to 36. MQ is x, PM is x, so x times x equals to 36. X times x is x squared, so x squared equals to 36. Here we'll take out of this equation and find again that x equals to the square root of 36, that is 6. X equals to 6 units in its length. Here x equals to 6. Here x equals to 6. In the next step, we'll implement the Pythagoras theorem on this small right triangle MBQ. According to the Pythagoras theorem, in any right triangle, the score of the hypotenuse equals to the sum of the scores of the perpendiculars. So, in the right triangle MBQ, BM squared, that is the score of the hypotenuse, is equal to BQ squared plus QM squared. Repeat again. In the small right triangle BMQ, according to the Pythagoras theorem, BM squared equals to BQ squared plus MQ squared. BM is the missing side, so we leave it as it is. So it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, it is 16, plus MQ squared. We just write down formula that MQ equals to 6. So therefore MQ squared is 6 squared, it's 36. So in total we should know that BM squared equals to 16 plus 36, that is 52. So BM squared equals to 52. Here we'll take a root out of this equation and find again that BM equals to the square root of 52 units in its length. The hypotenuse BM equals to the square root of 52 units in its length. In the next step, we'll implement the Pythagoras theorem on this big right triangle APM. In the right triangle APM, here by PT is the version from Pythagoras theorem. So in the right triangle APM, according to the Pythagoras theorem, AM squared, that is the square of the hypotenuse, is equal to AP squared plus PM squared. Repeat again, that big time 8 p.m. according to Pythagoras theorem. AM squared is the square of the opposite equals to AP squared plus PM squared. AM is the missing side, so limit is CT, so it is AM squared equals to AP squared. AP is 9, therefore AP squared is 9 squared, that is 81, plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, we found out that AM squared equals to 81 plus 36. 81 plus 36 is 117. In total, we found out that AM squared equals to 117. Here we take out all those equations and find again that the opponent AM equals to the square root of 117 units in its length. This is the opponent AM. This equals to the square root of 117 units in its length. Our task is to find out the area of this green shape. The green shape is actually the right triangle A and B. And we know that the area of any triangle equals to the base of the triangle times the height over 2. We choose the base as BM. It will be equal to the base BM times the height MA over 2. So the area of the green right triangle A and B, the area of the green shape is equal to the area of this green right triangle A and B and the area of this green right triangle A and B equals to the base MB times the height AM over 2. Okay, again, the area of the green shape is the area of the right green triangle A and B, and the area of the right green triangle A and B equals to the base MB times the height AM over 2. We already found out that A and B equals to the square root of 52. Times the height AM, that equals to the square root of 117 divided by 2. So in total, we found out that the area of the green shape, that is the area of the right triangle A and B, is equal to the square root of 52 times the square root of 117 over 2. We have the algebraic identity that says that the square root of A times the square root of B is equal to the square root of A times B. So we use this algebraic identity here, and we get that the square root of 52 times the square root of 117 is equal to the square root of 52 times 117 divided by 2. 52 times 117 is 6,084 over 2. So the square root of 684 is 78 over 2. 78 over 2 is 39. So I should know that the area of the green shape, that is the area that we are looking for in this question. It's equal to 39 square units in its size. And again, the area of this green shape, that is the area that we are looking for in this question, is equal to 39 square units in its size. So finish with the second question. The next step, as far as the lecture, we'll start with the first question, of course. The first question, our test is to find out the area of this pentagon ABCDE. So what is a pentagon? A pentagon is a closed flat shape with 5 straight lines, with 5 straight sides and 5 interangles. This is pentagon ABCD. There's 1, 2, 3, 4 sides and also 1, 2, 3, 4, 5 interangles. So our test is to find out the area of this pentagon ABCDE. This gives us the question that this is a right angle, ED equals to 1, DC equals to X, CB equals to 1, AB equals to 1, and EA also equals to 1. Again, our test is to find out the area of this pentagon ABCDE. So first of all, we join points E and B together by straight line, and we join points A and C together by straight line. In addition, we did another construction, that is to say we extended side VA by straight line in such a way that the extended part will be equal to X. So the extended part AM equals to X unit in itself according to our construction. When we extended straight line by straight line, the result BM is also a straight line. So if you focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to all three. All three says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? We have this angle, that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points E and M together by straight line. We join points E and M, we created the right triangle EMA. In the next step, we prove that those two right rectangles can go into each other according to side angle side rule. So why those two right rectangles can go into each other? First of all, side AM of the right triangle EAM is equal to side DC of the right triangle EDC. They are both equal to X and therefore they are equal to each other. In addition, those two angles are both right angles and therefore they are equal to each other. And finally, side EA of this right triangle EAM is equal to side ED of this right triangle EDC. They are both equal to 1 and therefore they are equal to each other. So actually proved that those two right rectangles can go into each other according to side angle side rule. That is to say, we should prove that those two sides and the angle that is included between those two sides in the right rectangle EAM is equal to those two sides and the angle that is included between those two sides, that is the right angle, in the right triangle EDC. And therefore, we should prove that those two right triangles can go into each other according to side angle side rule. And again, we should know that the right triangle EAM can go in, this is the sign of can go in, to the right triangle EDC according to side angle side rule. And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. That is to say, the area of this right triangle EAM is equal to the area of this right triangle EDC. The area of the green right triangle EAM is equal to the area of this right triangle EDC. So if we define, so if the area of this when I time EMA is equal to Z coordinates in size, then there on this when I time EDC must be also equal to Z coordinates in size, because they have the same areas. Likewise, from the fact that those two right intervals can go into each other, we will derive that side EM of this right line EAM is equal to side EC of this right line EDC. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore the two corresponding sides, that is to say EM and EC, must be also equal to each other, and there so EM equals to EC. In the next step, we calculated the graph of this line segment MB. Coordinate is very easy to say that MB in total equals to MA plus AB. MB equals to MA plus AB. So MA equals to MB equals to AM is X plus AB. AB is 1 minus X. So in total MB equals to X minus 1 minus X. X minus X is 0, so we have to agree with 1. In total we found that MB equals to 1 unit in its length. In the next step, we prove that this big triangle MEB can go to this big triangle EBC according to side rule. So why those two triangles can go into each other? First of all, MB equals to CB equals to 1. They are both equal to 1 and therefore they are equal to each other. In addition, side ME of this side MEB is equal to side EC of this side ECB. According to we found out that ME equals to EC, because those two triangles can go into each other, we derive that ME equals to EC. And finally, EB is a common side that belongs to both triangles, so we can write down that EB equals to itself as a common side that belongs to both triangles. So in total, we found out that all the three sides of this triangle E and B correspond equal to the three sides of this triangle EBC. And therefore, those two triangles can go into each other according to side rule. But again, we found out that triangle E and B can go into triangle EBC according to side rule. In the next step, we calculated the area of this triangle MEB. The area of triangle MEB equals to the base of the triangle, that is MB, times the height EA over 2. So the base MB equals to 1, the height EA also equals to 1, divided by 2. 1 times 1 is 1, divided by 2 is 1 half. So in total we found out that the area of this triangle MEB equals to 1 half square unit in size. But because of the fact that those two triangles can go into each other, they must have also the same areas. Therefore, this triangle EBC must be also equal to 1 half. So in total, the area of this triangle EMB, this is 1 half, plus the area of triangle EBC, this is also 1 half, is equal to 1. Repeat again. The area of triangle EBM, this is 1 half, plus the area of triangle EBC, this is also 1 half. In total, it is 1 half plus 1 half, that is 1. So the sum of the areas of those two triangles, in total, it is equal to 1 half. But this is the big quadrangle EMBC. The big quadrangle EMBC consists of those two triangles, triangle EMB and triangle EBC. And therefore, the area of triangle EMBC, the area of the big quadrangle EMBC, that consists of those two triangles, must be equal to the sum of the areas of the two triangles that it consists of. That is to say, it must be equal to the of this side EMB, this is 1 half, plus the of this side EBC, this is also 1 half. Okay, again, the area of the big quadrangular EMBC must be equal to the sum of the areas of the two triangles that it consists of. That is to say, it must be equal to the area of triangle EBM, that is 1 half, plus the area of triangle EBC, this is 1 half. 1 half plus 1 half is 1. So in total, if you want to know that the area of this big quadrangular EMBC equals to 1 half to 1 square inch in size. Okay, again, if you found out that the area of triangle EMBC equals to 1 square inch in size. And again, we already found out that the area of the big quadrangular EMBC equals to 1 square inch in size. The big quadrangular EMBC consists of two other shapes. The big quadrangular EMBC consists of this green outline EAM and this quadrangular ABCE. And therefore, the area of the big quadrangular EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of line EMA plus the area of this quadrangular ABCE. And again, if you want to know that the area of the big quadrangular EMBC is equal to 1, must be equal to the sum of the areas of the two shapes that it consists of. It consists of the green rectangle EAM and it consists of also the big quadrangular ABCE. So from this equation, we derive that the area of triangle EAM plus the area of quadrangular ABCE equals to 1. Okay. Area of triangle EAM plus the area of quadrangular ABCE equals to 1. But according to our definition, the area of this green rectangle EAM equals to Z, square inch inside. So we can substitute the area of triangle EAM by Z, and get the total that Z plus the area of quadrangular ABC equals to 1. Okay, if it again Z plus the area of quadrangular ABC equals to 1. Our task is to find out the area of this big pentagon ABCDE. Actually, the area of pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of this triangle plus the area of this quadrangular ABCE. Pentagon ABCD consists of only those two shapes, and therefore the area of pentagon ABCD must be equal to the sum of the areas of the two shapes that it consists of. And again, the area of pentagon ABCD must be equal to the sum of the two shapes that it consists of. It consists of the green rectangle ADC, and it also consists of quadrangular ABCE. According to our definition, we already found out that the area of the green rectangle equals to Z. We can substitute the area of the green triangle ADC by Z. So it is Z plus the area of quadrangular ABC, DABCE. So the area of pentagon ABCDE equals to Z plus the area of quadrangular ABCE. But we already found out that Z plus the area of quadrangular ABC equals to 1. So we can write here that Z plus the area of quadrangular ABC equals to 1. And from this long equation, we derive that the area of pentagon ABCDE equals to 1. If you don't know that the area of the big pentagon ABCD equals to 1 square inch in size. The area of this pentagon ABCD equals to 1 square inch in size. So we finished with the first question. The next step actually present to the second question and repeat on the solution of the second question. In the second question, our task is to find out the area of this green shape. The green shape is actually triangle A and B, so we have to find out the area of the green triangle A and B. In the drawing, we have a circle. Inside this circle, we have the green triangle A and B. We know that AB is the diameter of the circle. In addition, we know that line side AP equals to 9 units in its length. Line segment BQ equals to 4 units in its length. PQ is tangent to the circle at point M. Again, our task is to find out the area of this green shape, that is the green triangle A and B. So first of all, we implemented all 7 in our drawing. According to all 7, if you try triangle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle called AB is the diameter of the circle. This is triangle ACB that subtend on called AB, that is the diameter of the circle. Therefore, triangle ACB is equal to 90 degrees in its size. So if you implement all 7 in our drawing, we have triangle A and B that subtend on called AB, that is the diameter of the circle according to all this given situation, and therefore according to all 7, triangle A and B must be equal to 90 degrees in its size. In the next step, we define this angle PAM as alpha. So the right triangle APM, the big right triangle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, which is the sum of the angles in a triangle. PQ is actually a tangent to the circle, therefore it is absolutely a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to all 3. So which angles we have at the upper side of the straight line PQ at point M? You have this angle is equal to 90 degrees minus alpha. This is the right angle according to all 7. Plus this angle BMQ total must be equal to 180 degrees according to all 3. All 3 state that the sum of the angles on one side of the straight line is equal to 180 degrees. So in total we get that 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ in total must be equal to 180 degrees according to all 3. 90 degrees plus 90 degrees is 90 degrees, so 90 degrees plus 90 degrees is 180 degrees. So 180 degrees plus angle, missing angle BMQ plus minus alpha in total must be equal to 180 degrees. Here we have 180 degrees on both sides of the equation, so 180 degrees we get cancelled. And we have to only if angle BMQ minus alpha equals to 0. Here we added alpha to the equation, if we found out that the missing angle BMQ equals to alpha degrees in its size. This is the missing angle BMQ is equals to alpha degrees in its size. In the next step, I shall prove that those two triangles are similar to each other according to angle similar to all. That is to say, the big right triangle APM is similar to this small right triangle BMQ according to angle similar to all. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. And finally, those two angles are both equal to alpha, and therefore they are equal to each other. So I should prove that all the three angles of this big right triangle APM are correspondingly equal to all the three angles of this small right triangle BMQ, and therefore those two right triangles are similar to each other according to angle similar to all. So for the English, we found out that that time APM is similar. This is the same similar to that time BMQ according to Engel similar at all. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AP of the big right angle APM or side MQ of this small right angle BMQ is equal to side PM of the big right angle APM or side BQ of the small right angle BMQ. Again, from the fact that those two right angles are similar to each other, we will derive that side AP of the big right angle APM or side MQ of the small right angle BMQ is equal to side PM of the big right angle APM or side BQ of the small right angle BMQ. AP is 9 over MQ. MQ is the missing side, so it's as it is. And is equals to PM. PM is the missing side, so it's as it is. Over BQ. BQ is 4. So total, if you all know that 9 over QM equals to PM over 4. Here, of course, multiply this equation. And I should found out that AP times BQ equals to 9 times 4, that is 36. So again, MQ times PM equals to 36. Again, MQ times PM equals to 36. MQ times PM equals to 36. In the next step, we define the center of this circle. This point is point O. So OA is the radius of the circle that we define as R. OB is also the radius of the circle that is equal to R according to our definition. In the next step, we did the construction. First of all, we join points O and M together by a straight line. OM is of course the radius of the circle that is equals to R. The radius OM that is equals to R, the radius OM is going to point M, that is the point of tendency of tangent PQ with this circle. And remember, your radius that is going to the point of tendency, then tangent PQ will be perpendicular to the radius MO according to rule 1. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did the construction, that is to say, from point O, that is the center of the circle, we go perpendicular on AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point O and AP. This point is point L. By doing this construction, we created the big quadrilateral LOMP. The big quadrilateral LOMP, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth integral. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth integral must be equal to 90 degrees in its size. So inside quadrilateral LOMP, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So related to this quadrilateral LOMP, it's a rectangle because it has 4 right angles. Quadrilateral LOMP is a rectangle. In the next step, we did another construction, that is to say, from point B, we draw perpendicular on the radius OM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. When doing this construction, we had the small quadrilateral SBQM. The small quadrilateral SBQM, we have 1, 2, 3 right angles, and therefore this fourth angle must be equal to 90 degrees in size, and therefore quadrilateral SMQB is a rectangle because it has 4 right angles. We note that the opposite sides of a rectangle are parallel to each other. Again, the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, then the straight line itself, AP, must be also parallel to the other straight line. Therefore, AP is parallel to OM. AP parallel to OM. The next step, we copy the two parallel lines AP and OM, and also there are also AP in the equation implemented all 50, the new drawing. This is line 7 AP, this is parallel to OM. This is the radius AOB, that is the from the original drawing. Radius AOB cuts the two parallel lines at points A and O. Those two angles are defined as corresponding angles and are located between the parallel lines AP and OM, therefore they are equal to each other according to Rule 50. Rule 50. According to Rule 50, corresponding angles between parallel lines are equal to each other. Line A is parallel, the drawing line A is parallel to line B. Line C cuts the two parallel lines at those 2 points. Those are angles alpha and beta that are defined as corresponding angles and they are located between the parallel lines A and B. Therefore, they must be equal to each other and their sizes. That is to say, alpha equals to beta. So, can implement Rule 50 in our drawing. We have those two corresponding angles that are located between the parallel lines AP and OM, and therefore they must be equal to each other and their sizes. So if you define the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other according to Rule 50. So if you have angle PAO equals to beta, this is angle PAO is equals to beta, and also found out that angle MOB also equals to beta. This is angle MOB is equals to beta. So in the right triangle ALO, this angle equals to beta. This angle equals to 90 degrees, and therefore this previous angle must be equal to 90 degrees plus beta according to the rule that the sum of the angles in the triangle is equal to 180 degrees. Likewise, in the right green triangle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this previous angle must be equal to 90 degrees plus beta according to the sum rule that says that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we prove that those two right triangles can go into each other according to angle side angle rule. So what those two right triangles can go into each other? First of all, those two angles are both equal to beta, and therefore they are equal to each other. In addition, those two sides AO and OB, they are both the area of the circle that is equal to R, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So if you prove that those two angles and the side that is included between those two angles, that is R, in this right triangle ALO corresponding equal to those two angles and the side that is included between those two angles, that is also R, in this right triangle OSB, and therefore those two right triangles can go into each other according to angle side angle rule. So again, if you know that right triangle ALO can go into the right triangle OSB according to angle side angle rule. And from the fact that those two right triangles can go into each other, we know that side ALO of the right triangle ALO is equal to side SB of the right triangle OSB. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore the two corresponding sides, that is to say ALO and SB, must be also equal to each other in their legs. So LO equals to SB. So if we define the length of side LO as x, then the length of side SB must also equal to x because they are equal to each other. We know that the opposite sides of the rectangle are equal to each other. So in the big rectangle LO and P, side LO must be equal to the opposite side PM, but LO is x, therefore PM must be also equal to x and its length. Likewise, in the small rectangle SB QM, side SB must be equal to the opposite side MQ, but SB is X, therefore the opposite side MQ must be also equal to X units in its length. We already found out that MQ times PM equals to 36. MQ is X, PM is also X, and MQ is X, PM is X. So in total, X times X equals to 36. X times X is X squared equals to 36. Here we to wrote out the equation, find out that X equals to the square root of 36, that is 6. So here X equals to 6, and here also X equals to 6. In the next step, we implemented the Pythagoras theorem on this small right triangle BMQ. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Therefore, in this right triangle MBQ, BM squared, that is the square of the hypotenuse, must be equal to BQ squared plus QM squared. And again, in the right triangle, the right small triangle ABQ, BM squared, that is the square of the hypotenuse, equals to BQ squared plus MQ squared. BM is the missing side, so limit is it is, so it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16. Plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So we should know that BM squared equals to 16 plus 36. 16 plus 36 is 42. So BM squared equals to 42. We will took out of those equations and find out that BM equals to the square root of 52 units in its length. This is side BM, equals to the square root of 52 units in its length. In the next step, we implemented the Pythagoras theorem in this big right triangle APM. According to the Pythagoras theorem, in this right triangle APM, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. Again, in the right big triangle APM, in the right big triangle APM, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. AM is the missing side, so limit is it is, and it is equals to AP squared. AP is 9, therefore AP squared is 9 squared, that is 81, plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, we should found out that AM squared equals to 81 plus 36. And again, AM squared equals to 81 plus 36. 81 plus 36 is 117. So in total, we should found out that AM squared equals to 117. Here we took out all the equations and found out that AM equals to the square root of 117. So the AM equals to the square root of 117 units in its length. Our task is to find out the area of this green shape. The green shape is actually the right triangle A and B. So the area of the right triangle A and B will be equal to the base MB times the right AM over 2. And again, the area of the green shape is the area of the green right triangle A and B. That is to say, it is equal to the base MB times the right AM over 2. MB is equal to 52, AM is equal to 117. And again, MB is equal to 52, AM is equal to 117. Divided by 2. We have the algebraic identity that says that the square root of A times the square root of B equals to the square root of A times B. And therefore, the square root of 52 times the square root of 117 will be equal to the square root of 52 times 117 divided by 2. 52 times 117 is 6084 divided by 2, and the square root of 684 is 78 divided by 2. 78 over 2 is 39. So in total, we should find out that the area of the green shape, the area that we are looking for, is equals to 39 square inches in size. Repeat again, the area of this green shape, that is the area that we are looking for in this question, is equal to 39 square inches in size. Okay, thank you very much.